In today's video, we talk about rendering the running path for our running videos for Singapore front runners. What do we mean by a running video? Well, if you remember the video that we created for the first part of the Sungei Bedok run, we started a video with a map that shows the location of our start point. Then at the end of the video, we have another map that shows the location of the endpoint. Right, this is the 3D map we're talking about. We have a 3D map at the end, and we have a 3D map at the beginning. But notice our 3D map is fixed at a specific location, either Bedok North MRT or Bedok Food Centre. For a running video, which we'll create in the next part of the run of the Sungai Bedok run, we will animate this. Right, so imagine that this dot here will run all the way from Bedok North MRT all the way until Bedok Food Centre. It will be animated on a map. We will put this map on the bottom of the bottom half of the screen here, and then we will show our running videos on top. That's why we are now talking about creating this running video. How do we render a 3D map such that this gold sphere is going to run through our path, right? Right. So I have some updates. Let me just give you some information on how it's done. This is Unity. Unity is the tool that we use together with the Mapbox SDK for rendering the maps at the beginning and the end of the previous video. Let me show you what I did with this Unity SDK. When I run this project, notice that there is a pink cube. The pink cube lands exactly at the Bedok North MRT station. And you can see in our script that it's telling us that the Bedok North MRT station is located at x equals 0, y equals 0, z equals 0. Why is this significant? Well, the problem we had so far was that we are used to rendering our map positions in latitude and longitude. But Unity only recognizes its own internal coordinates. X equals to 0, y equals 0, z equals 0. It's a very whole number. The question we have is that how do we translate a real world latitude longitude into Unity coordinates? What does a real world latitude longitude look like? If you look at our map, you can see that this is the latitude longitude of the Bedok North MRT station. It's a very long number. It's about 1 degree north of the equator, which is where Singapore is located. That was a question we had in our last video. How do we translate this into a map, into a Unity coordinates? Unity coordinates are going to be 0, 1, 2, and all that. Let me show you the script that does that. We have a script here. Let's say under the project assets, we created a script called run script. And if you open it, we can see this. Now, we have recorded the Bedok North MRT station here. This is coming from Google Maps. We just selected Bedok North MRT, copied the latitude, longitude. Eventually, we're going to populate with the Bedok Food Centre, which we also copied from Google Maps. Now, how did we get this script? Well, let me explain in a while. This is coming from the examples from the Mapbox SDK. I'll show you in a while. Okay, important thing to notice is that okay, we'll skip start for now. There's a problem with it. We won't use it. Okay, let me just close my notifications. All right. What's happening is that when we have a this is the script that we run inside Unity, right? We have a script here that says whenever we're rendering the map, this function is called this is C#.NET code. This update function is called every time we render a frame in Unity. What we'll do is that we'll call this function called onMapReady. onMapReady is our function here. What do we do at every frame? Well, every frame we will assign a latitude-longitude coordinate. In this case, for this example, we are using the latitude-longitude of Bedok North MRT. Remember, we copied this from Google Maps, right? Now, to convert it to unity coordinates, we simply call this map behavior, Mapbox map, map information, convert lat long to position, and then you pass in the latitude-longitude coordinates. Then we print out the x, y, and z value with a marker. Remember the pink box? So the pink box will now be set to that location, the x, y, z location. This is important, right? We have now figured a way to convert a latitude longitude like the Bedok North MRT into a map box coordinates x, y, and z, right? And if we look at the run log, we can see that in the console here, and then I filtered by run script to see only our messages. We see that x equals 0, y equals 0, z equals 0, which is correct because our map is now at the same location that we provided here. Essentially, we are mapping the same location as the map. That's why x, y, and z are all 0. To verify that it's really working, we change it. We change it to the latitude and longitude of Bedok Food Center, which we copied from Google Maps. Let's see what happens when we run this. Let me clear the log. Notice that when I save the file, it's going to recompile the script. Okay, the log is cleared. Then we just run this. Remember that the pink square, the pink cube was right in the middle below the sphere. Now it's no longer there because it's somewhere else. As we move to the location of the Bedok Food Center. And where is Bedok Food Center? It's this location. You can see the x is now 4.2. Y is 0. It's on the horizon is on the flat plane. And z is now minus 1.8. Which means that it's now um, 4.2 units away. X, I guess, is to the right or to the left. Then Z is minus 1.8, 1.9, which means that Bedok Food Center is way behind our camera. It's behind us, right? Yeah, and this works. How did we get this script? We got this script from the Unity SDK. If we go into the Unity Mapbox SDK on GitHub, and then scroll down a bit, we can see that there is a sample code. Go down some more. Okay, this is a lot of information. And okay. Okay, actually it's here. So it's under one of the examples. If we look at the GitHub page, we see that there is a here, place a game object at latitude longitude. Yeah, so the idea is this: we need to get a map information from Mapbox behavior, and then after that we can convert the latitude longitude into into the unity coordinates. How do we do this? We go into this page here, and then we see this script. This was the exact script that we copied over. Only thing difference is that they use Mapbox map.initialize, and then they set it such that when the Mapbox map is initialized, it will call map ready. However, it wasn't working. That's why I had to change it. If you look at our script works a bit differently. Instead of calling Mapbox map.initialize, we don't. When we run this, it will tell us that Mapbox map is empty, it's null, and therefore this won't work. I'm not sure why. It appears that Mapbox map is not created yet. Maybe I need to set the creation sequence correctly so that this script will run after the Mapbox map has been created. But that's okay. We can kind of brute force it. What we did was that we put it into the update function. Remember, the update is called every time the frame is rendered. Well, why don't we do it that? Instead of just calling on map ready once during initialization, now we call on map ready at every update of the render of the frame, right? Now, and this is where we do the conversion. Now, Mapbox map might still be null if our map is not initialized yet. That's okay. It will just report an error here, and then it will just suddenly quit this function. It will not continue execution. But if it happens that Mapbox map is properly populated, it will continue running this code, which is why we see the XYZ coordinates. This happens only when Mapbox map has been properly populated, is non-null. Then it will do this conversion, and it will print the XYZ, and it will move the marker to that location, right? Yeah. So according to the official example, we're supposed to call initialize the initialize event, set the event such that it will call on map ready when it's initialized, but it's not working. Therefore, we put it into update, which is fine also. Yeah. This is important because we will now get our running path from the FIT file. What is this FIT file? In one of the earlier videos, we said that this is the FIT fit file viewer. We loaded in the fit file. This is coming from Garmin Connect. Our Garmin Connect records the latitude longitude coordinates of our run through our Garmin Forerunner watch. So when we load it into the fit file viewer, we will get the raw data, and the raw data shows us that yes, it has the latitude and longitude for every single point during our run. You can see our timestamp, and you can see the latitude longitude. Therefore, to get the actual coordinates for our run, we can we can export the records from the fit file, and we'll get this. What do we do with the latitude longitude? Well, we will now pass it to this function here, convert lat long to position. This will give us the XYZ coordinates that are applicable for Unity. Remember, these are Unity coordinates, no longer latitude longitude. And then we can use it to do our manipulation in Unity. We could set a marker position. More likely, we'll use it to set an animation. We have an animation for our like say for our sphere, right? If you go to animation, we can see that it's setting a position. Right now, it's doing a bounce animation. It's going into it's bouncing from z equals, sorry, it's bouncing from y is 0.2 to 0.04. That means it's actually dropping from a height to a lower height. We will change this. We will have x and z coordinates reflecting the x and z coordinates from here, right? We'll take that long, convert it to Unity coordinates, and then we will take the x and z and put it into our animation here. Once we do that, our sphere will be following our run path according to the map, right? Are we going to manually copy and paste all the coordinates into this animation? Well, we'll do some exploration. Previously, we saw that the animation files are actually quite straightforward. They are text files. For example, if you look at the run sphere animation, run sphere animation is here. Open it with Visual Studio Code or any text editor. This is a this is actually a YAML file, YAML. We can see that the coordinates are here. We saw earlier on that y is 0.2, then y becomes 0.04. So in theory, we could edit this file, and then we could populate this file with all our latitude and longitude converted to Unity coordinates, and it will work. Yeah, I'm just hoping that the other things won't change. There's the in-way, out-way. I'm not quite sure what it does. Maybe it has to do with the smoothing of the dots, the smoothing of the spline. But I'm just going to ignore that for now. I'm just going to set the XYZ value according to the translated latitude longitude, And I'm going to change the time. So this tells us that at time 0, 0 is the number of frames. We set at this value. Then at the 15th frame, we set it at these values. So those will change, right? And hopefully this works. And I'm hoping that these things don't matter, in slope, up slope, all that. Well, let's find out, right? Yeah, so we have a way to populate the latitude and longitude that we extracted from our Garmin Forerunner watch using the FAT file format, the FIT file format. And then from FIT file format, we have a way that we can copy and paste this into a script that will convert into Unity coordinates, right? Then from there, we can populate this Unity coordinates into the animation file. And there we have it. That's the animation for our run. And hopefully that works. It sounds quite simplistic, but let's see what happens. The animation, this is animation for the sphere. There's also the animation for the camera. The camera right now is it's just doing a simple drop. If you look at the run camera animation, we see that it's just doing a okay. It looks a bit different, but let's see. Okay, run camera. Okay, but if we look at if we follow the run camera animation, it's just simply doing a drop. Oh, it's actually following a spline. Yeah, so there's a spline. Remember that we use a camera path that tracks along a spline, and then we set the spline position from 0 to 1. So this animation is saying use a spline position from 0 to 1. Okay, this will be tricky. So let's look at the spline. The spline is run camera spline. Is this the one? Or is it the other one? Yeah, I'm trying to figure out which one is the right one. But we can see some coordinates in our spline. Yeah, we can see some position on that. This could have to do with the spline, or maybe something else. I need to explore this. But the point is that we'll position the camera a bit behind the running sphere. So the sphere will be in front of the camera. The camera will be slightly behind the sphere, and then we'll track the sphere as it runs along the running path. So this is where we are we're looking on the running path in perspective mode. We're not doing a top-down view, but we're doing like a perspective view, like a first-person view of the running path, right? Yeah, so that's what we plan to do in the next couple of videos. But before I finish this, let me explain how I created all these, because the steps to create this are not quite so obvious. And one of the tricks I had to do was to set the reference correctly. But let me explain what I did. Now, what I created was that notice I've replicated these things. The CD machine camera, it now has two versions: a start end as a run. Spline, the camera spline also has a start end and a run. Then a sphere has a start end and run. What is a start end versus run? Well, start end is the one that we saw in the video. I'm going to keep it as is. I'm not going to touch it. Therefore, I copied it and I made another version that I called run. Right. Right now, the start end camera is disabled. We're only using the run camera. That's why it's tracking the run. And the run camera is following the run camera spline. Right. Yeah, and then the start end sphere is also missing because we are now using the run sphere. Right. Now, how did we add the script? The script that we saw earlier on. This script that will convert a latitude longitude into these three values. The way I did it was that first we created a game object. Just right click, create empty. It will populate our project with a new game object. We'll call it game object. I renamed it as run script because we're going to attach a script to it. The over at run script, I did an add component and I selected new script. I called it run script, right? Then when we go into the run script, we can just double click. It will launch Visual Studio Code to edit or whatever text editor you have. And then I just put in this code that I've tested earlier. Notice that there are some references to this. It will require the Mapbox base module and you require Mapbox example, right? I will show in a while how I set the references, because if you compile this, you will try to run this, it will say that Mapbox example, Mapbox base module are not defined. Therefore, we need to set the reference before this will run in Unity. But two things I'll show right now is that notice that the two public fields in our run script. There is a Mapbox behavior. There's a marker, which is a transform kind of object. When we put in these two things, it means that we are going to plug in an actual Mapbox map, and we are going to plug in an actual 3D object. You can see it here. If you go into our run script, now you can see that it tells us that it requires a map. That's why we click and selected map, which is our Mapbox object here. The second thing that it needs is a marker. Marker is the thing that will follow along the position. Well, we just simply set to a run marker. What is run marker? Run marker is just simply a right-click 3D object cube that I created, and I renamed it as run marker, right? Just make sure that run marker is big enough. I set it to 0.05 so that it's big enough to be visible. If it's too small, it will not be visible. I set the color to pink. Yeah, that's mostly it. Yeah. Then after that, when the script runs, it will move the marker to that position that we've seen earlier. Now, we talk about the script, right? The script has a reference to these modules, Mapbox base module and Mapbox.example. How did we set the reference? Yeah, this was a tricky part. What I did was that I had to right-click under the assets. I right-click, create a scripting assembly definition. Then I renamed it as run assembly. So let me show you the assembly definition. So this is the assembly definition. I'm calling it run assembly because that's the module name, the DLL name for our project. Important thing is that first you need to do this override references. You must click this. Once you click override references, you will be able to see the assembly definition references. This says that this code that we're running, the run script, will make use of these two modules, right? So you just click plus, then you just select from a list, okay? Make sure that we select these two modules. There must be a Mapbox base module and there must be a Mapbox examples. Once we do this, our script will compile correctly. It will no longer complain that Mapbox base module is missing or Mapbox example is missing. It will be defined, and then our script will be able to run. So this was the most tricky part of the whole setup, making sure that we click override references and then we set in these two things, right? And make sure it's under assembly definition references, not assembly references. It's kind of confusing. Yeah, so make sure that we do this. And then it runs. That's it, right? So what we'll do next is that we will go back to our fit file. We'll use a command line tool to dump out the latitude-longitude. There are plenty of command line file export tools for fit file. So I can dump out the latitude-longitude from this. Then I will create a simple script that will import the numbers into our run script, right? So imagine that instead of doing one latitude, longitude here, we will have a whole series of latitude, longitudes, and we will convert the whole series of latitude, longitudes into Unity coordinates. Once we have the Unity coordinates, we will run it, and then we will have we will capture it from a console here. then we'll be able to populate that into our animation, right? If we follow the run sphere animation, we'll be able to do the X, Y, and Z positions. Yeah, Y won't change, but X and Z will change. How do we plan to do that? Well, we plan to edit the animation file. We saw earlier on that the animation file, which is here, run sphere animation, has all these X, Y, and Z coordinates. Therefore, I will just simply add, copy and paste, add all the X, Y, and Z coordinates into this file. And then hopefully it will do the right animation for the run sphere, and the run sphere will follow along our running path. Then we need to do the same thing for our run camera. Our run camera also has its own animation. Let's try this. Yeah. Right now, our animation is just following a spline. This is following a run camera spline. If you look at the run camera spline, yeah, it's following these coordinates. So there's yeah, it's just following these coordinates. Okay, now I remember. The run camera spline is actually stationary. There's only one position, right? But the run camera will move. That's because when we use our run cinema camera, okay, our run camera, cine machine camera, we say that the run cine machine camera is pointing at the run sphere, right? That means you always rotate to keep the run sphere in the center of the frame. Our run sphere follows animation. That's why as the run sphere drops from a high position to a low position, our run cine machine camera will also follow it. Even though it's stationary, it's at a fixed position, our run cine machine camera will turn to face the run sphere to keep it in the center. Right? That's why it appears that the camera is moving, but it's actually not. It's just rotating to point to the run sphere, to keep the run sphere always in the center. Well, when we do the run animation, it'll be different. The run cine machine camera will have to move, and it will have to follow along with the run sphere, not stationary. Therefore, the run cine machine camera will have to move, and it will have to, yes, it will still point at the run sphere, but then our spline will be different. There will not only be one spot. There will be a few locations, and this will be similar to the XYZ values that we get from here, except that we offset it a bit. Remember that we need to move the camera a bit behind the run sphere so that we can see the run sphere in front of us, right? Yeah, therefore we need to do some computation, make sure that maybe the Z value is somewhere behind the run sphere. That will allow us to see the run sphere in the view of the camera. Yeah, it sounds very complicated, but I'll explain more when I actually program this, right? Yeah, so that's it for today's video. I will see you in the next video when I talk about how I'm going to do the running path. How do I render the actual running path? And how do I make sure the camera follows along it? The next video is in the video description below. See you later. Bye.